So, going through the MolochVault challenge from Quill, uh, we'll run down through the code here, and then we'll go through and implement the attack. So yeah, just as we go, drop any questions that you might have in chat, and I'll talk through that as we go, and we'll see if we can hack through this thing and get it implemented. So the challenge itself gives us some hints. If you take a look at the page on the actual challenge, the goal here is to steal at least one way from the vault. And so they also deployed the contract code to the Golari testnet because this involves more than just the code itself in the smart contract. Uh, the challenge itself says that it's deployed on a testnet because it heavily relies on extracting data from storage. So we get a little bit of a hint there as to what we should be looking for when we're going through this. So let's take a quick look at the code itself. In this contract, we have a couple different immutable variables that are set. It looks like this is used in send grant, and then it's set within the constructor. Then we also have this immutable variable, which doesn't have a very helpful name, the hy7uih, which is used in a function of also complicated naming. So we can already tell that some of the naming conventions in this contract will make this challenging and might not be helpful. So we'll just have to get comfortable with that as you go. And then we have another private and immutable variable here. So a couple different immutables that are set down in the constructor. Something to note too, like this contract isn't really following best practices in our patterns, right? Normally you want to have all of your storage variables at the top. They have a couple floating storage variables throughout this contract. The constructor is at the bottom. Normally the constructor is at the top of the function set. So a couple different things that are muddying looking through this contract, but of course in auditing, there's no guarantee that what you're auditing is going to follow, the best standards. We have this mapping here, real hacker, which is interesting, and address to bool. Oftentimes you see address to bool mappings used in access control, so we'll keep a look at that. They have this cabal struct, identity, password, as well as a string for a public question, a string array, excuse me, for question, which we also saw down here is set in the constructor, and a array of these cabal structs. So we're going to take a look at those as well. So there's a couple functions at the top, but let's start by looking at the constructor because that's where a lot of these immutables are being set. So I'm going to close this so that we can see a little bit more. It gives us some intelligence, perhaps irrelevant. There was Kodak Rome, who also is the author of this, tweeted something here. If you follow this tweet, it's basically just a string that's not super helpful to us. I would say that it's likely a bit of a head fake. But if anybody's curious, this is what was in the tweet right here. So you can see it there. All right, what's actually happening here? In the constructor, we're passing a bunch of different strings. So we have the string for Moloch pass, which is being used to set this HSAH variable. They're encoding that string and then hashing it, which we also see in code packed. So there's doing a lot of encoding of strings. This Moloch variable is basically like owner, but it's encoding the message.sender and then hashing it to store it there. This string array for B is used to set the question value. So question 0 is equal to the first string value in this string array, or the first value in the string array, and question 1 is set to the first, so we know that there's something interesting happening there. And so, and then what's interesting here is this HY variable is the encoded pact of question 0 and 1. So they're packing together the two values from the second input B and throwing it into this value here. I think I might have heard somebody come on the mic. Is there a question or anything that might be popping up? No? Okay, cool. So then what we have here is it's setting up some of these cabals using a for loop, setting some passwords based off of the addresses that are passed in A. And then the string pass with a bunch of S's is also used as like the passwords in this setup. So the payable array A and the string array pass is being used to set up this set of cabals that are used in the application. We can see that there's this initiation function. So the goal of this is to steal one way. So we want to look at this contract and find where can we steal way out of this contract, or where is this contract sending way? And so when you look at send grant, you see here right away that there's this grantee.call, and it's going to send a value of one way along with this grantee.call. So this line here, line 39, allows us to send way. So our question becomes, how can we hit this line and send ourselves way? This require statement here is what's gating it. This is a public function, but there's a require statement that's essentially providing access control here. So what this require statement is saying that the message.sender either has to be the deployer. We saw that Moloch was set to the deployer down here in the same way with the hash of the encoding. We see the same pattern here. Or the message.sender has to be part of this real hacker array, which we saw earlier on. So also, like, these require statement messages for when the require fails aren't helpful. So anyways, a lot of head fakes in here. But we need to get access to real hacker. So real hacker, let's see, we know it was defined at the top, but where is it used? In send grant, and then, okay, real hacker is set to true within this UHER778 function. So let's take a look at what's going on here. This is also a public function, and here we're passing our own string of, or our own array of length 3 of strings to this function. And then it's doing a couple different things. So how to open the reference like that to see real hackers. So I'm using VS Code. If you hold down Command or Control and you hover on function name or a variable name and you click on it, it'll give you its pointed definition. For any storage variables, I'm using the Ethereum plugin or the Solidity plugin for VS Code. And so it'll tell, if you click on a storage variable, it will tell you where that storage variable is used throughout the contract. So that's how I'm doing that. And it's actually really helpful. So usually, like, if I'm auditing something and I just want to, or if I'm doing like a Securium race or something like that, can just quickly go through it and understand the code by clicking. Yeah, so it's probably doing jumping. So if I go down here, right, it'll jump to the variable if I'm clicking someplace that wasn't the point of definition. If I click at the point of definition and it's been used elsewhere, then I see the overlay. And that's happening because I have an extension in here. Let it come up. I'm forgetting the name right off the bat. Which one of these is it? Yeah, so Solidity Visual Developer. If you add that one in, I'm pretty sure that's where that functionality is coming from. Cool. All right. continuing on, we're taking a look at this function here, which is, we know down here, if we get to the bottom, we'll be a part of this mapping. And once we're a part of this mapping, we can take way out. So we're passing in a bunch of strings. Here, I'm going to start using some comments since it's not very helpful, but this first variable is check the balance of this contract before this function executes. And we see that this variable is also getting used down here. And then this, which is being used in this last require statement, is check the balance of this contract essentially after execution of the above logic, right? So what this requirement statement is saying that after execution of this function, the balance of the contract should be one way more than before it was called. So we know through this that we're going to have to provide some way to the smart contract in order for this last require statement to come. So when we implement our hack, we know send at least one way to this contract. And that's likely why it's payable. Okay, what are each of these require statements doing? This variable, actually both of these variables we know are set in the constructor. And what it's asking to do is it's saying that when we encode the first string that we pass in our string array to this function, and then hash it, it needs to be equal to this immutable variable that was set during the constructor. Basically, it's following the same pattern as, oh, sorry, my screen's lagging a little bit. Following the same pattern as we saw down here. So this HSA H variable, we need to figure out what was malloc pass. So I don't know if anybody has some initial ideas on how we can get the value of malloc pass, but essentially we need open secret, and I'm spelling it the way they spelled it, 0 to be equal to malloc pass, the constructor variable that they passed when they deployed the contract. And then also message value has to be less than 3 gigaway. So that's just a constraint. So we know that while we need to send at least one way, we can't send more than 3 gigaway. Again, these messages aren't very helpful for when we're trying to decode this, but we'll go ahead, and if we do run into those, then that's fine. So here, this is interesting. So we're doing the encode pact of secret 1 and secret 2. So this is Copilot helping me out a little bit here. But if we go back down to our constructor, we know that this variable hy7 was set by encoding question 0 and question 1. And question 0 and question 1 are equivalent to B0 and B1. So we can even make this a little bit more descriptive. Say open secret 1 should be equal to B0, the constructor variable, and open secret 2 should be equal to B0 or B1. That's where we're at from this line. And we're just giving the same inputs. It's getting encoded and packed the same way and then hashed the same way. So we would get the same output. Okay, this third and kind of final require statement that we got to get through. It's saying that when we encode open secret 1, which we said should be equal to B0, the encoding and hash of that cannot be equal to the encoding and hash of question 0, which we know question 0 is equal to B0. So we now know that this line, open secret 1, cannot equal B0. So we have a little bit of a conflict between the second require statement and the third require statement. So how do we resolve this conflict? And this is where this hack is actually, there's some interesting aspects to it, and like kind of one of the core points that you have to understand in order to get through this CTF. And that's, we are using this encode pact. So in Solidity, there's several different ways to encode and decode. You can encode with signature, you can encode with like the actual function call, you can encode normally without anything, or you can encode pact. Encode pact, basically what it's doing is, instead of encoding its inputs and padding those inputs with zeros, it will pack it all together right next to each other and remove any padding. And you have to be careful when you do this, because you're concatenating things which, when they're unpacked, when you're decoding something that's been packed together, you can have unexpected results. And so essentially what they're looking for here is an understanding of how encode pact worked. So it will help, we'll need to figure out what values were passed in the constructor, and we can do that because this contract was deployed, and we'll do that in a moment. But let's say that the B0 is, or just more specifically, question 0 was 1, 2, 3, a string that said 1, 2, 3, right? And then let's say that question 1 was 4, 5, 6. Because they're encoding this packed together, you would have the exact same result if question 0 was 1 and the rest was 2, 3, 4, 5, 6, because they're going to be packed together and then hashed. So what's being hashed is these being encoded and packed together. So that allows us to make it so that our open secret 1 is not equal to B0, but still have this require statement pass, because what we're packing together will end up being the same as these when they're packed together, even if the individual values themselves are different. I'll pause for a second if there are any questions, but that will become a little bit more clear once we also open up the values that were passed in the constructor. Okay, so it seems like no questions. So I'm going to pull up the challenge itself. So that we can grab the address that this was displayed at. And let me just add this real quick to the recording. So I'm going to just switch screens that I'm sharing with you all real quick so that you can see here. This was deployed at this address on Golery. So when we go here, this is something that you can do on a lot of blockchain explorers, but we're going to take a look at the contract on Etherscan. And when you scroll down, what you can see is the constructor arguments. And this was what was passed into the constructor when it was deployed. And this decoded view is telling us what those actual values were. So malloc pass said bloody pharmacist. The B string first argument, it said, who do you serve? And then see this comma here. So the B0 was who do you? B1 was serve with a question mark. And so those are the core values that we're looking for. So if I switch back over to the VS Code, we can now give ourselves a little bit of a mapping as to what our attack is going to look like. All right, let me pull this up. So I think now is probably a good time for us to start implementing this hack. So pulling up VS Code, what we know we need to do is let's pull up the attack page. I created some default pages for us. So we'll do the standards. We got SPDX, license, identifier, pragma, solidity. Okay, it's auto-filling that, likely because that's what MolochVault is using. I'm going to import that contract. Then let's say contract Moloch. Let's call it Moloch attack. So we need to create a exploit function. And in this, we're going to pass the target, which is going to be the MolochVault address. We'll make this payable because we know we need to be sending some way around. So then we need to call the MolochVault. And we're gonna, MolochVault is defined like this. This is the contract name. If we just go back to it real quick so you can see it. That's why I'm writing it that way, contract name, right? So we have the MolochVault, and it's going to be, we're gonna cast the target, which is the MolochVault, to that. And see, Copilot's helping me out a little bit here. ER778. And then we need to pass, we'll use the default that it's providing so that we can go in and pass that. But we need to pass 3 strings in an array. And it's yelling at me because this is a payable contract. And so we need to cast target to be payable as well. Any questions here? Okay, so obviously this isn't going to work yet. We need to define what these strings are so that we can get through the UHER778. So again, we know open secret 0 needs to be equal to Moloch pass. And Moloch pass, we know when it was defined in the constructor, was this bloody pharmacist string. So we're just going to take that, we're going to drop it right into the first value in our array, pharmacist. Then this one, we want the B0 value and the B1 value, which was who do you and serve. Now we know to get past this third require statement, we're going to need to move around those last 2 strings. So let's just say I'm going to cut this and paste it here. So we have who and then space do you serve. And this is all concatenated because there's no space in the input that they put into the constructor. And if you added a space, this would come out the wrong way. So you need to have it exactly like this. And so I just want to make sure that we're clear on this for everybody. We're moving this part of the string to our third input because this third require statement here is saying that our inputs can't be exactly the same as the input that went into the constructor. And this encode packed vulnerability is why we're able to pass our string this way and have it still pass. If they weren't using encode packed, if they were just using encode, this wouldn't work. Okay, cool. I haven't seen anything in the chat, so just gonna keep on churning through this. So we also know that it wants to see that the contract has at least one more way now than it did at the start of this call. And so here, let's see, payable message.sender.call. As always, when we're doing this, we're looking for any external calls. Is there a place to inject some logic? This is going to be an external call to our attack contract, which is what we're writing right now, because our attack contract will be message.sender, and they're going to send one way to us. So when this happens, they're going to be sending one way to us, but it needs two-way. So we're going to just implement a little receiver function so that when we receive one way from this contract, we send two-way back to the target contract. And so the way that we can do that is by implementing a receive function. For anybody who's not familiar, receive, notice I didn't have to put function in front of it. Receive is a function that's can be put on any contract, and it's the function that defines how any logic that's executed when this smart contract receives Ethereum without a function being called. So if it calls exploits payable, and if you send ETH to exploit, that'll be fine. But if you just send ETH to this contract without also defining a function selector that you're trying to execute like exploit, it will fall to the receive function and execute there. If you don't have a receive, but you do have a fallback, it'll fall down to the fallback function. And what we're going to do here is, okay, we know that we're going to payable, we're going to say target. This should be coming, we're going to be called from the target. We're going to say transfer, and we want to transfer two-way because they just transferred us one way. They need to start with more than one way. And I guess since this isn't a public variable, we can just make this message.sender, and that's fine. Normally, you wouldn't want to do this, right? Like your attack contracts themselves can be exploited, right? So you want to make sure you're protecting your exploits. I mean, we're not exploiting anything in real time, right? But let's say you're doing MEV or anything like that, right? You got to make sure that the contracts you're using themselves are protected, and this is very unprotected, but we're just developing it this way for the sake of this CTF. So what is this doing? Let's kind of go through the logic flow. We call this function. It tracks the balance of the contract. Our strings, we know from the constructor, should pass these three require statements. The contract then tries to send us one way. When this call happens, it hits our receive, and our receive sends two-way back to the vault. So now the vault has one additional way that it didn't have ahead of time. So this last require statement should pass, saying that the balance of the contract has incremented by exactly one way. And notice that this is a hard conditional and not a soft conditional. Then we'll have access to the real hacker, message.sender equals true. And then once we're a part of that, we should be able to call send grant, and send grant will then be sending way to grantee, and grantee we're just going to pass in as ourself. So let's add that line here, and the goal is to steal at least one way, but remember, as of right now, they have an additional way. So we're going to need to take two-way out of this contract. So we're just going to go like this, MolochVault. Then again, payable target, send grant, payable, and we don't want it to be message.sender. Let's say, well, we could make it message.sender. And then, but let's not do that. Just again, from a best practice perspective, let's make it say address this. So we're going to send the way back to this address. Theoretically, you could send it, and we're going to duplicate this twice, right? Because so this will give us one way, and then this will give us the second way, which will make it so that we've stolen one way. But there is a problem here in this implementation, is that right now, anytime this contract receives anything, any amount of ether, it's going to send two-way to whomever sent it that ether. And this is only sending us one way. So this can be solved with like a simple conditional. You see this in like a lot of reentrancy attacks. So this is a little bit like we only want to send way back to them when we receive ether in a specific scenario. So return ETH equals true. We're going to set this conditional. Then we'll say after this first call, we'll set return ETH equal to false. And then here we'll just say if return ETH, then send this way. All right, did not mean to do that. So now the flow is that when we call this first line, in order to get access to the mapping that allows us to call send grant, we will, when they send us the way, we'll send two-way back. Then we'll set this to false so that whenever we receive any future ether, this is skipped over. We receive the ether into this contract, no problem. And then this ether has that contract. All right. That's generally the hack. Now, there's some things that from like a real world use case usability, you want to make sure that you can always get ether out of your contract, right? So we could implement a constructor, define an owner, and say that only the owner can pull it out. Also, we could skip this and just say send it to message.sender, or again, implement an owner. But for the purpose of this hack, we're really interested in the fact that you can pull things out of the constructor arguments when something is deployed, and you can exploit the ABI.encode pact, and that can be used in unexpected ways, right? So you can shift things around so that your variables aren't exactly equal to the input and still have the same variable or the same value come out of that ABI.encode pact call. So let's go ahead and implement a test, and then this also will get into a little bit of like cool Foundry stuff, because we're interacting with a contract that was actually deployed, right? So let's set up our Foundry test. I'm looking for Copilot to help me out here. Yeah. Import. We're going to start by importing Forge standard library, right? Then we'll import, this is source MolochVault, and then also source attack. Then we'll just say contract hack is test, right? So we're saying is test because we're borrowing all the standard library that Foundry provides us. In tests, you can use your public or your storage variables loosely, right? We're not worried about storage and gas efficiency. So to make these accessible in our test cases, right? Did I spell this with 2 A's? Yes, okay, we only want 1 A. This will make these variables available to all of our test cases, and for anybody who hasn't used Foundry before, your test cases are different functions, and so those functions need access to these storage variables. And then we'll also define a hacker. You can create addresses using makeAddr and then passing a string. Then we need to set up our tests, right? So setup is a reserved function in Foundry, and this will be run before every single test. Now we need to define the vault, and this is the contract that we're attacking. This isn't just like a new one that we're deploying. We want to, okay, question. Line 11, those should be attack. So I called this file attack.sol, but the contract itself is Moloch attack. So maybe that's a little bit misleading. That was just me going quickly, but the contract itself is called Moloch attack, and so that's why here it's Moloch attack. Yeah, actually it has to be the contract name. The file name it won't recognize, right? So the file name we use in the import, but the contract name, we're defining a variable of this contract type. Remember that you can define several different contracts in a single file, right? So I could go like contract random, right? And then this contract would also get imported when I import the attack contract. So anytime you're specifying like within your contract, the variables, you want the contract name. Cool. So now we want to define our the vault that we are actually attacking, right? And we know that this is going to be a payable address. And then what is the address? So we want to pass in the address here that's just actually on chain. So I'll grab the address that this was deployed to and then just drop that in right there. And so now what we'll do is when we actually run this test, we're going to use a fork of the Golari blockchain locally. And then that way, when we're using the fork, there will be something which exists at this location, right? Okay, then we're going to go, we're going to start prank and do hacker. So start prank in Foundry is a way to like simulate the address that is making the calls. So again, this is like all in Solidity. We're testing in Solidity, and normally you can't change the calling address within a function call, right? That's you know that the EOA that initiates the function call is the one that is making the call. So start prank is a way to change the context of the caller. And then we're gonna, this is essentially deploying our attack contract. And then we wanna give our hacker 1 ether. All right, we need a space there. And deal is just a way to, in your test cases, seed your different accounts with ether. So now let's test the attack. In Foundry, all of your test functions need to be public or external. It needs to be possible to call it externally. And so we need to steal one way. So we're just going to keep track of what was the balance before the attack. And we're going to say address vault dot balance. So we'll store that so that we can ensure that this is actually working. And we'll log it to the console so that we can see it easily. And say starting balance, pre-attack balance. And then we'll actually run the exploit. So it's getting a little bit ahead of itself, how that is, but yes, we want to call attack exploit with the address of the vault, but we need to also send some way. So value 3-way. And this is, you can define specific aspects of your call this way in Solidity. So value 3-way, that's what we're sending to our contract. And then we'll just say console.log balance after attack, and then address vault.balance. So we'll be able to see that in the console, but we also want to like have an assertion to make this clearly a test. So we'll say assert less than the address vault.balance should be less than the pre-attack balance. So that's the assertion we're going to make in this test. Okay, we'll see how this goes when I run it. There might be a bug or so in here, but we'll go ahead and debug it as we go. So how are we going to do this? We're going to say forge test. We'll add our verbosity so that if there's something wrong, we can see it. And then we need to add a fork URL, right? And that fork URL is what's going to, oops. All right, well, I hit enter too early, so this is going to fail on us. I'm going to do Control-C. What we're going to do, what this is essentially doing is this is forking the Goerli testnet to our local environment so that we can test our execution as though we were executing it on Goerli itself. So I'm going to be using Alchemy. You need a RPC to fork the latest, and I'm just going to use Alchemy. I have a account set up with Alchemy, and let's see what happens. So now what it's doing is compiling contracts. Since we haven't compiled them before, you could also do that using forge compile. And then it's also going to take a look at the status of the Goerli testnet, fork that locally on an anvil, which is the local chain that is provided by Foundry. All right, so it's not liking my, okay, well, I already saw it in this recording, so I'm gonna need to change it anyways. I'll just directly put it in. Let's try this again. Looks like it's probably not seeing the environment variable. Let me grab my Alchemy key real quick. Bear with me. Any questions as I do this? Has this made sense so far? It's been awfully quiet. All right, got some typing. That's good. Okay, cool. Good to hear. All right, I'm almost logged in. I'm gonna just grab my Alchemy key and drop it in, and then I'll change it afterwards. You guys are all going to see it, and then it's going to be on the recording as well. So it's all right. All right. Let's give this a try. Yeah, I'm going to record these. So I'm going to start tossing these up. This is actually the first one that we've recorded. Oh, there's passed the wrong test name. This is the first one that's recorded. I'm going to backfill. I didn't have a chance to record the other ones. And so we'll start recording these so that anybody who misses it can go on and take a look at what we talked about throughout the call. Okay, finally. So our attack passed. It had a starting balance of 9,999,28 and then finished with 2,7, and our balance decremented appropriately. So that's pretty much the hack. It's an interesting one. This one is, again, talking about understanding the context outside of just the code, right? When we're thinking about security, when we're developing, we have to consider more than just what's in Solidity. We have to know that the variables that we're passing to our constructor are public and can be seen by other people, and that's not a secure way to set up our contracts by passing what should be secrets through to the constructor. Yeah, that's one important takeaway from this. And then the other important takeaway is just making sure you understand how different encodings work. And if you're using encodings that you know that the encoding is working the way that's expected and that it can't lead to a vulnerability. Encode pack can be great. It can save you some space, but it has to be the right thing for you and your specific use case. All right, that's a wrap. Are there any questions? If not, next week we'll just tackle the next CTF that's on Quill, and we'll go through the next one. All right, we'll close it there. Thanks, everybody. Really appreciate everybody joining, and I'll talk to you soon. Have a good weekend.